Good afternoon now. This is Carlos Huggins speaking from National Physical Laboratory in Teddington in the UK, and I'd like to welcome everyone to this webinar on generating robust and relevant data for tribological performance, presented by Professor Mark G. So, excuse me, too fast on the buttons there. Let me spend a moment talking through the agenda so that people understand what we're doing. As I said, first of all, the agenda outline is this. I'll give a brief overview of NPL and say something about Mark. Secondly, I'll hand over to Mark, whose main section will maybe last about 50 minutes. He has 3 sections to his talk. And what we're going to do is, after each section, we'll have a little break where we'll take written questions and Mark will answer them by over the audio. So everyone should be able to communicate questions in using your chat dialogue. If you can do that, we have quite a lot of people on the line at the moment, and it wouldn't be practical to try and take verbal questions. So after maybe 40 or 50 minutes of that give and take, Mark will have finished, we'll have taken all the questions and answers, and I'll go to a wrap-up where we'll deal with the next steps and we'll talk about, and I'll close the webinar, which hopefully will be just before 1 o'clock UK time. So, let me move on then to say something about Mark. I'm not going to read this slide out, but just to say he's an NPL Fellow in our Materials Division, recently elected a visiting professor at the University of Southampton, and is very well established and known in this field. I should mention all the slides will be available to the interested hereafter, and any questions that are passed on and are answered we'll communicate afterwards. So about NPL. This is the UK's National Standards Laboratory, founded over 100 years ago. As you can see, it has about 450 specialists in measurement science, and we interact with a lot of universities, a lot of businesses. And as of all the national measurement institutes, our particular one is to deliver the measurement capability that underpins the UK's prosperity and quality of life. But of course, being a national institution, we have many international links, and this webinar is reaching out to several countries, and by the time other people have logged in, hopefully a good few more. Now, it's now by my clock about 3 or 4 minutes past 12, so I'm hoping we have the main audience in, and I'm going to hand over to Mark to start his detailed technical talk. And there you are, Mark. You have the microphone.
Right. Good morning. Wrong. Good afternoon, everybody. It's only just afternoon, so forgive me for that mistake. And I think you've seen everything on my title slide. I just wanted to say that this event is being co-sponsored by the IET Professional Network for Tribology, and we've had significant help from them in terms of publicity for this. So moving on, I'm going to, this is a little bit more of a detailed agenda. I'm going to talk about wear and friction, what they are, why we want to do tribological testing, how we should carry out testing, the effect of humidity as an example of control of test conditions, surface examination techniques, and we're then going to have a break and we can take questions then, and I'm going to go on then with a few examples of recent testing that we've been carrying out here at NPL, then have another break, and then finally mention a bit of publicity really for a project that we're undertaking with EU funding that may interest you. I'd just like to point out that I don't actually have any content on lubrication tribology. When we started off in Tribology some years ago now, we decided that we would focus on dry wear and friction, and also things like abrasion and erosion rather than lubrication, and that was because there was already quite a large number of people working on lubrication in the UK. So, moving on. Wear and friction then, and the reason I put this in is it's quite important to have a good understanding of what wear and friction are. So wear is defined, and these definitions here are taken from ASTM. Wear is the removal of material from contacting surfaces in relative motion, and friction is the force generated by those contacting surfaces that resists that relative motion. They are both complex phenomena dependent on many different parameters. There are many different types of wear. Wear is a major and ubiquitous source of losses to commerce and industry, and it affects most industrial sectors, and I've just picked out a few there: transport, mineral extraction, and manufacturing. Friction needs to be controlled, but is not necessarily a bad thing. Indeed, wear is not necessarily a bad thing. If you actually want to machine materials, then you want controlled wear, in fact. But friction in particular, if you didn't have brakes, if you didn't have good high friction soles on your feet, we'd all be in a bit of trouble. Both friction and wear have impact on sustainability, efficient energy generation and use, and competitiveness of industry. Just a few examples here, images of where friction and wear are important. So you've got the wind turbines here, and a lot of us know that the gearboxes in particular in these wind turbines are critical, and they don't yet have the durability in terms of tribological performance that we would want. Generation of cans for our fizzy drinks and whatever is a highly tribological issue, and it always amazes me that you can go from that to that in a very short space of time with a rate of about 400 per minute, which is quite amazing. I've mentioned shoes. This is a camshaft. This is coated by a DLC coating, in fact. This is digger teeth. It was actually a digger on my lawn at home. We have an extension built, and the wear to these teeth is quite incredible in real mineral extraction applications. This is a hard disk. This is a hip implant, and this is a brake. They're all examples of where the tribological performance is critical. I'm just going to go through a few of the different wear mechanisms that are commonly encountered using these diagrams here. And the first two are abrasion. Abrasion is actually one of the commonest mechanisms of wear, and there are two cases here. The first of them is abrasive wear from moving contact with hard, sharp, granular materials. Some people would call this three-body wear because the particles are loose. The second one is abrasive wear from hard, sharp particles trapped between moving surfaces, and some people would call this two-body wear. Moving on, adhesive wear. This is where you get one nominally flat surface moving over another. One of the important things to realize is that even though you think it's flat, it's not really flat, and typically between two surfaces you get 4 or 5 different points that are carrying most of the load, and at those points you can get phenomena like welding of the asperities together, and then you get removal of material and you get wear processes that take place. Fretting comes from small oscillatory movement between relatively smooth surfaces, but the emphasis on this one is that it's small motion. Cavitation erosion is when you get collapse of vacuum vapor particles, bubbles in a fluid, and the stress waves that are generated through that cause damage to the materials that lie underneath, and It can be quite severe actually. You would think that bubbles don't create much damage, but they can do. And a typical well-known example of this is propeller blades for ships. Particulate erosion is also critical, and this is where you get hard particles in the stream of fluid hitting a surface and causing damage to the surface. And finally, the final one I've got listed here is the release of particles from the surface as a result of fatigue processes, repeated rubbing backwards and forwards, or even in the same direction, of an asperity or protuberance on the surface. And you often get that sort of damage occurring in ill-designed bearings and things like that. So I just wanted to go through those because one of the critical elements in carrying out wear testing and even having a hope of generating good data is to recognize the mechanisms that you have. So why do we want to carry out wear testing? There are several drivers here. One of the main ones is we want to reduce losses from wear. We want more efficient and more capable machines. We want more sustainable use of materials, and we want more competitive manufacturing. This diagram here I quite like. It's from an old German standard, and it doesn't exist anymore, unfortunately. I like it mainly because of this diagram of this truck that's trundling through the forest here, and that represents a field test. You've got your system and you actually try it out in practice, and you find after a while it fails, and then you try and work out why it fails. The difficulty with that is that usually it is so complex trying to work out what's happened that you don't necessarily get the fundamental information you want. You can go from that all the way through this sequence of examples to laboratory tests, and laboratory tests are much better controlled. They are cheaper normally. They are less complex. But the big question is, do they really simulate what you want in the field? And that is a very big question. So, yes, I've asked one of those questions already. Before you want to carry out a test program to get good data from tribological testing, you need to answer two questions. What are the conditions in your application? A short form of that question is, what is the issue? And the second question is, how do you then reproduce this to the required degree in the laboratory? So, short form of that is, what is the answer? You also need to have a pretty good idea of how to analyze the results you get and use them in practice. And tribology is actually one of these areas where there's actually no replacement for expertise, and that can be the expertise of the person that's carrying out the program of testing, or you talk to people that do have that expertise. So I posed another question on the previous slide, which was, what is the required degree? And there are several possible answers to this. The first of these is that you actually try and replicate every detail you can in the laboratory, so that you know you're going to get the right answer when you do your testing. And there are some very large corporations and institutes that do exactly this, and they know they're going to get reasonable results. And one of the downsides of that is that the test systems they use tend to be rather expensive and rather complex to use, as I've said earlier. The other approach, which is used by a large number of people, is that you relax the conditions to achieve a simpler test. But this really needs a lot of understanding about what's happening, so that you know which of your test conditions that you can relax and which ones you can't, and you can have some surprises here. One of the checks on that is that you look at your results and you check that the major features of the wear are reproduced in the laboratory in comparison to the application. It's very important to use the correct test to do this, and there's a cautionary tale here. We did a survey about 15 years ago to find that about 70% of the wear problems in industry, and this is a very broad brush here in industry, are abrasion and erosion. It's surprising, therefore, that about 80% of wear testing, as published in the literature, is done using pin-on-disc testing. And even where you've got sliding wear, pin-on-disc testing is probably not the right approach to use. Reciprocating backwards and forwards motion is probably better than the uniaxial, always in the same direction motion that you get with pin-on-disc testing. So what are the factors in practical simulation of a wear test, a friction test? And this is a little bit daunting, in fact, but you do need to consider a lot of these aspects, and the list is actually longer than this. So you need the microstructure and materials to be similar. The sample surfaces at the points of contact should have a similar shape to those in the surface application. The pattern of contact should be similar, intermittent or not. The contact pressure should be similar to that which occurs in practice. The pattern of movement and speed should be similar. Debris is often generated and must interact with surfaces in the same way as in the application. This is something that some people overlook from time to time, but it's absolutely crucial, because the debris can push surfaces apart, so you're not really looking at the contact of one surface with another. Acceleration of the test is tempting, but you've got to be very, very careful about doing this, and you need to preserve a similar mechanism to the mechanism that you get in the application. The reason it's tempting is that a lot of applications where tribology is important are very long term. Just think about an internal combustion engine and its lifetime of 10 years or so. And if you want to replicate wear of that, you don't really, and you can't carry out a test for 10 years. So how do you deal with that? So the crucial thing that you always need to make sure is that the mechanism of wear in the test should be the same as that in the application. How do you do that? Well, we'll come on to that, but a very important thing you need to do is to use examination of the surfaces and microscopy and that sort of thing to do that, and we'll come on to that in a moment. The test variables that you apply are critical, and you have to use the right test variables. You have to adjust the right test variables, and you have to make sure that you consider all of these very carefully. So it's one of the things that is needed is to develop robust test procedures. It's my belief that you do need good standards for testing. We need to consider the test variables in the design of tests. I said that already. And parameters include, but are not, this is not a complete list, are the load, the speed, the materials, the test environment, the contact geometry. Humidity is a surprisingly important one, and the dynamics of the test system, or indeed the dynamics. I'm talking about things like inertial loading and things like that here are surprisingly important. An example of matching the application to the test is given here, and this is a firm that was producing concrete tiles for roofs, and they used a tungsten carbide cobalt component called a slipper blade to actually form these tiles. And the big problem they had was that they got a lot of abrasion from sand and other hard particles in the mortar mix that wore the component, and they wanted to improve the component lifetime. So we did a program of testing. We realized it was a low stress set of conditions, conformal geometry. We looked at what's called the ASTM G65 rubber wheel test. We modified that somewhat. One of the main things we did was we changed the pH of the fluid that we used in that test. We also modified it so that you could carry out the test wet. For those that know, that's normally a dry test, but we had it wet. And we got, if you look at the two micrographs, the top was a component, a section from a component extracted from a real slipper blade, and the base image was a test sample, and we reckon we got an almost exact match between the one and the other, and that gave us a lot of confidence that what we were doing was sensible. And we found, talking to the firm, that we actually got quite a good correlation between our lab tests and field data, and that's also another check you can make sometimes. It depends on your circumstance. A cautionary tale here, of course, is that although we did all this work and it was quite a big problem, the research centre that we did the work for was shut down, and I don't think they ever used the results. So you're always affected by politics as well as sensible testing. An example of the effect of different test variables is humidity. I mentioned this, and it is quite surprising how big an effect you can have. This is alumina, submated alumina. So this is alumina on alumina, and there's water vapor in the air, and it's carried out in a pin and disc geometry, so you're rubbing a ball against a disc, and what we're measuring here is the wear scar that appears on the ball. And there's a huge effect, in fact. If you look at just the effect on the wear scar, that goes from about 1.5 millimeters up to nearly, well, 4.5 millimeters. And that doesn't seem quite as bad. That's only a few factors. But if you actually convert that to the volume of wear that takes place here, then there's a huge difference between 80% humidity, where the volume is 0.05 millimeters cubed, up to down to 3% humidity, where it's 4 millimeters cubed. So several orders of magnitude. And the reason for that is that at low humidity, as indicated here, the micrograph shows that you've got a lot of fracture going on, whereas at high humidity you've got this dark phase formed. We found that this was aluminium hydroxide, and it protects the surface. So a critical difference in the mechanism that you get, that you need to look at, that means that high humidity is much better in this situation. You might say, oh, ceramics, we all know that there's an effect with water on ceramics, but if you look, oh, and this is more stuff on the mechanism. I forgot that this slide was here, to be honest. This shows a little bit more about the mechanism. It's wear debris that reacts with the water to form this softer phase that fills in the gaps in the hard surface. And you can see a micrograph. We've used adhesive tape to pull off the aluminium hydroxide here, and we've done some nano indentation that proves the properties of the two phases. This is a slide I was thinking was there, and it isn't just true for ceramics. So here you also get an effect of silicon nitride and silicon nitride. Silicon nitride on alumina, but with steel there you also get a big effect, and notice the huge effect for steel on steel, and also if you look at the literature for tests on brass, copper, all sorts of other materials, you often get an effect of humidity, so that's something that's important to note. There are a lot of standard tests around nowadays. Again, about 15 years ago, we did a survey of this, and we found about 400 standardized tests in the literature issued by the various standards bodies, and on tribological issues there are probably more now. This just lists a few of the more common ones. ASTM G2 committee is a committee that's devoted to wear testing, so that should be a first source to go to. But SEN committees and ISO committees also are producing standards relevant to tribological testing. There are many more than the ones listed here, and it's important to note that these probably don't suit your particular application, but you should use these, if you can, as a basis for your specific requirements. So I mentioned that one of the important things you really ought to do is to use examination of the surface to check that the mechanisms that you're getting are sensible and match up with your application. There's a huge range of techniques nowadays. We're getting better and better at getting more and more information out about what's happened to surfaces. But there should be a basic principle here that you use the simplest technique first and stop as soon as you've got the required information. And just looking at your surface is the simple thing that everybody can do without any expensive kit, and it tells you a huge amount. And you can go through many other techniques, so optical microscopy, 3D optical microscopy is coming in nowadays and is very important, and I've got a slide on that. Scanning electron microscopy, profilometry, surface analysis, TEM, but these are getting quite expensive, and you need to talk to people that have that sort of kit. We're fortunate here, being NPL, that we have a lot of that, so we're one of the people that you can come to for that, of course. So an example of just optical microscopy is these two micrographs. This shows what's called the bright field micrograph, and you think here, this is an aluminum surface, by the way, and this is a transfer layer on the surface, and you think that this is this was rubbed with steel, by the way, and you think the steel has transferred to the surface. We use cross polars here, and this is on most optical microscopes, to show that in actual fact what you think is the steel transferred to the surface is actually iron oxide, and you can now see the brown color that's been revealed. And if you get the conditions right, you can see that this is a dark shade of brown, as it were, as well. So this is definitely iron oxide, and you've identified that very simply from optical microscopy. And this shows the slide I mentioned earlier. This is 3D optical microscopy, and here you can see the results of a test. This is looking at the steel ball that we rubbed against a DLC coating. This is before the test, and this is after the test, and you can see the wear scar here. You can see there's a transfer layer, and you can see that there's some material that's built up on the surface. What you can do with these microscopes is you can look at height maps. This is a height map before wear has taken place. You can get a height map after wear has taken place, and you can then subtract these two images. You can do something called image correlation, data set correlation I've called it there, and you can subtract the two, and the result in this case is this micrograph here, where the red is the true wear volume, which you can determine pretty accurately with this instrument that we've used here with an accuracy of about 10 nanometers. I should say precision, not accuracy, actually. And that's the red, and the green is actually the built-up material around the edge. So this is higher than the original surface, and this is lower than the original surface. And you can see that in a profile that's taken on that line there. So this is the wear, and this is the built-up area on the surface. So we can, using this sort of technique, get very accurate measurements of wear, and that's becoming increasingly useful. Another approach to the similar sort of thing is 3D SEM stereography, and the idea here is that you just use an SEM and you can carry out measurements by taking images at two different tilt angles, and you can then use automatic image correlation to give a height map, and this shows the image superimposed on the height map, and this here shows you the color-coded height map directly. you can then do all sorts of analysis on this. And this was actually a scratch on tungsten carbide cobalt. And this shows you the different scratches with different number of passes in the same point. And as you might expect, the scratches get deeper with the deeper number of scratches. Right, I'd like to break there, and I think I'll pass back to Carlos and we'll take some new questions at this point.
Thank you very much, Mark. This gives Mark a moment to maybe have a drink of water and gather breath. But I'd like to invite our audience, if they have any questions that come out of what Mark has just been talking about, please use your chat dialogue and send them in. We'll give you a minute or two to see what comes in, and Mark will attempt to answer them over the audio. At the moment we don't have anything, so I'll leave it to you out there in the great wide world to come up. It could be a specific technical question you want to follow up on something you've seen, or something a bit wider about something you feel could have been mentioned that wasn't. So please, we are here on receive. Okay, well, Carlos again here. We haven't seen anything come in, so I'm going to take that as an indication that Mark has done an astonishing discussion of the topic. Oh, hang on a minute. One has just come in. So that's excellent. Thank you very much. So in fact, yeah, the wonders of the internet. I'm just going to make sure Mark can see them, and then they'll hand over to him to answer them. So let me make sure I'm not on the line.
Right, yeah, okay. We've got a question from Alan Dunford, and the question is the additional material to the sides of the scratch, is that deformation of the original or deposition of of excavated material? No, in this, when you do a scratch test as a model of abrasion, which is what I use it for mainly, then it's just like an indentation. In fact, you get uplift around the edges nearly always. In this case, at the edges of the scratch in this material, you get a lot more deformation actually at the edges in some ways than you do in the scratch itself, and the grains are breaking, they're plastically deforming, and there's all sorts of damage there. So it's not redeposition of the excavated material. That tends to get scattered all over the surface. That is actually, and this sample actually was cleaned before we did this examination, so it's definitely not excavated material there. A second question from Stacy T-Boss is there a sensible way to estimate a start contact pressure for pin and disc test? You raise an important and quite difficult issue actually, in that there are basically two ways to do a pin on disc test. One is you try and get conformal contact. What I mean by that is you try and get a flat-on-flat contact over quite a large contact area. And there are some ways you can try and attempt that through things like self-adjusting sample holders that try and make sure that the orientation is correct for that conformal contact. That's surprisingly difficult. So what a lot of people do is that they use a known spherical contact surface and a lot of people actually use a very large radius for that spherical surface. So personally, I've used up to 300 millimeter contact surface. You can then use Hertzian contact theory to get an initial estimate of the start contact pressure, and that gives you an estimate. The problem with that approach is that almost instantly in a test you lose that because you get some wear and the contacts area changes with time. So there's not a simple answer to that, so even that simple question gives you some issues, and I've actually got some slides, I didn't have space to put those in, that illustrate that sort of issue. So if you like to get in touch with me directly, I can send you those. And the third question, and probably the final one, is from Madden Pi. Can change in humidity have an effect on lubricated tests as well? And my honest answer is I don't really know, but I suspect it does, because I think that the water does get embedded in the lubricant and can have a real effect on what happens. So I don't really have a definitive answer there, but I'm pretty sure it does. Thank you.
Okay, Carl's here again. I'd like to say thank you to all those asking questions. We're going to move on next to Mark's second part of the talk, and I'd just invite anyone who does have a question, feel absolutely free to type it in while Mark is talking, assuming you're one of those people that can listen and type at the same time. If not, push it through at the end. So I'm going to give the microphone back to Mark, and he'll carry on with his talk. Thank you.
Right, yes. I just wanted to make the talk a little bit more exciting from my point of view, actually, and hopefully from your point of view, by looking at a couple of examples of the sorts of things we've been doing more recently. So one of these is, well, I said recently, this is a little bit older now, but it illustrates that even in abrasion, and you can see this diagram here, this is where you've got a loose bed of abrasion of abrasive particles that's been pushed against the surface that causes wear to a surface. So, as I said, about 70% of wear issues in the industry are due to abrasion. We're looking at wear of tungsten carbide, cobalt, hard metals here. It's relevant to materials handling, mining, and so on. And tool materials from hard metals is a particularly important issue. So we modified the ASTM G65 test. We have a rubber lined wheel. We have a chute that we feed the abrasive down. In this case, we have a fluid feed, and we press the sample against the rubber lined wheel, and the abrasive goes down the chute and goes through the interface and causes damage to the sample, which we evaluate by measuring weight loss and looking at the wear surface. So this shows here changing two things, dry or wet, and changing the actual material of the wheel. In two cases we have a rubber rim, and in one case we just have a steel wheel. And you can see that changing those two parameters has a huge effect on the wear you get. Orders of magnitude change. So going from the wet steel test to the wet rubber test, you've got over 2 orders of magnitude of change in the wear magnitude. And you can also see that reflected in the wear mechanism that you get. So the wet steel looks a lot more confused and difficult to interpret what's going on. If you look at detail, there's a lot of fracture going on. There's a removal of chunks of materials, not shown in this micrograph really, but if you look in detail, that's what's happening. And it's a very rough and disturbed surface. The wet rubber test, by contrast, you're getting polishing of the surface in a lot of cases, and you get areas where some damage to the tungsten carbide grains is occurring, but it's a lot less damaging than in the wet steel. So what we're doing here is trying to tie up the microstructural mechanisms with the magnitude of the wear that we get. which is always a useful thing to do. I just wanted to mention also that we're doing some experiments with a Tribology test system. That's down here. This was developed here at NPL. And we carry out experiments on the laboratory bench. I say in situ in the SEM. That's the intention. We haven't got there with that yet. And the reason we're doing that is twofold. One is that it's appropriate for MEMS devices, but mainly from our point of view, it's so that we can look at the fundamental response of materials and tribological contacts at the asperity level. And we make arrays of tests, different load speeds, number of repeat scratches, and we measure friction and wear when we do that. And this just shows an example of the progression of friction on experimental coatings from carbon phosphide from Linköping University. One of the important things we do, as I said before, is we look at the mechanisms of damage. And here we're doing a single point model experiment traversing a diamond stylus, 20 microns, across the surface of tungsten carbide cobalt again. You can see the grains of carbide here. You can see the areas where there should be cobalt is etched away in this case. And this is relevant. It says current. That was a year or so ago now. TSB project looking at forming tools, and what we were trying to do was replicate the damage that we were getting from scratching in the application. And we saw mechanisms such as grain fracture, so you can see a big grain here which is fractured, fragmentation. There are areas where those grains are fragmented, and not in this diagram, but you can also see a lot of evidence for plastic deformation, these carbide grains. And the other thing that we do is repeated scratching, so you could look at the build-up of damage with a progression of the test. I'd like you to look at two micrographs now. This shows another scratch test. Here we've got 50 passes of 30 micron diamond indenter, and focus on this grain here. You can also see fragmentation, fracture, as I was saying earlier. This is actually plastic deformation here, and that's a very important mechanism for this material, and plastic deformation here as well. And if you look at the next slide, it's exactly the same area, and this is becoming an important area. So if I flick back to the other one, you can see that there's been a lot more fragmentation of the surface, and in fact a layer of this composite material, very fine scale structure, has built up, and we think this is important in terms of protecting the rest of the surface. In fact, again, you can also see some very severe plastic deformation down there. And finally, we have a relatively new tribometer now, which is a radically different design from most. Despite my remarks about pin and disc not being appropriate that often, we are using that here because we're trying to develop technologies that can look at the durability of surfaces. And the thing I'd like you to focus on here is this device here. This is actually a line scan camera, and as the test disc rotates, every line that is produced by the camera, that's the end of the camera, contributes to building up an image. And in actual fact, we could have one image that of the wear surface that gives you a complete time history of the wear surface during a test. And that's the important thing. This is online, real-time examination of the wear surface. It's not in situ, because that would mean looking through one of the test samples at the wear surface on the disc. But we're also developing techniques to do that, actually, using sapphire probe. So there's an example here of Tess 10mm steel ball on pink alumina disc. These are signals we looked at LVT to measure the total wear of pin and disc. We have something also called a chromatic aberration optical probe. These are very nice devices. They can run very fast, up to 100 kHz, and give you very accurate measurements of displacement. We've got an electrostatic probe. We're measuring applied load, we're measuring friction load, and as I say, line scan camera, stills and video. And this shows some examples. This is we get build-up of material on the surface, as I've indicated earlier in this system, and that's actually, if you look here, you can see that's this rust material again, and it shows a 3D optical micrograph of that surface. One of the advantages of this test system is the black line here is the LVT. That measures the displacement of the pin into the disc. The chromatic aberration measures just the displacement of the disc. So by subtracting those two, you can get, for the first time almost, an independent measure of the wear of the pin and the disc. And that's, this shows you the wear of the disc, in fact. And you can see that in this test, initially you get damage. Negative here is damage wear to the disc, and then you get an increase of the height of the disc as material builds up on the surface. And the blue line here is friction. A bit of a complicated diagram, sorry about that. The friction is about 0.7, which is typical for this sort of system. And here we have a video of one of the produced from this line scan camera. I'll bring the mouse back so I can run this. And so this is the surface of the alumina, and it goes in and out of focus. We need to refine the technology, but you can see that pits start appearing in the surface as the surface is damaged. Then these little black specks start appearing, which are adherent to the surface. And then later on we get these grey areas, out of focus at the moment. It'll come back into focus in a moment. Here we are. Build up on the surface, and then the remainder of this is the progression of these grey areas as we build up these transferred layers of iron oxide from the steel ball to the surface. And the importance of this is that for almost the first time, this enables us to see what is happening on the wear interface as it is happening, and that's tremendously important. I'm going to move on from that. It doesn't change that much for the rest of that video. But this just summarizes those results. So a still image from the start shows the original surface. Here we produce some pits in the surface. This is the low point of the wear to the disc. Here we're beginning to build up these layers which push the surfaces apart, and then this is towards the end of the test. This step here isn't significant, it's just an artifact in the measurement, but I hope you can see the power of that technique. And I will pause there and take further questions if you have some.
Okay, thank you very much indeed, Mark. We have had some more questions in while Mark was speaking. Congratulations to those who can do the typewriter stuff. So I'll let Mark pick out the questions that he wishes to answer, and of course if you have any more that you want to send in, please do so while he's speaking. We come from there. That's the first one.
Okay, so the first question I'll answer is from Stacey T-Boss, and she asks what is the importance of capturing the asperity level fundamental data. And I would say the importance of that is that it's an attempt to understand what's happening at the very fundamental level which underpins tribological interaction at the in the case of one surface sliding over another. The sort of philosophy there is that if we understand that, we can then start building an understanding of what happens at the macroscopic scale. That is a long shot, actually, and going from the one to the other, there are a large number of steps that intervene in that, and I expect we're going to be quite a few years until we have that in place. But at least we should have some lessons that we take from that to feed into actual understanding at the macroscopic level, which is important.
Okay, and Carty, I'll just mention to Mark that the next question comes in 2 bits, that bit and that bit. All right.
Yeah. Okay. Fine. So this is a question from Suresh Kumar, and I won't pronounce your surname, I'm afraid. In your rubber wheel abrasion test, I think the sample you used for testing is a metal. How about the case of ceramics? Do you think it follows the same trend as with a metal? I mean composite material, ceramics in different matrices, martensitic matrix or sinicic matrix. We have actually tested all classes of materials. By that I mean ceramics, ceramic composites, metal composites, and we get similar trends with all of those, that where you get there's some sort of relationship with the hardness of material. So as the hardness goes up, then the wear gets reduced. But hardness is not the only thing that defines wear. So if you take monolithic ceramics and compare them with tungsten carbide, cobalt, hard metals, you find that the toughness of the material is also crucial. And in fact, hardness, ceramics with the same hardness as a hard metal tend to wear far more, in fact, than the hard metal, and that's because they tend to be more brittle materials, and the fracture of the material comes in as a more dominant mechanism of wear. So you really do need to check and think about what's happening with the material. It comes back to mechanisms again. So I'd like to then move on to a question from Andrew Smith. Is it possible to video a wet contact? We haven't tried that yet, but we are going to shortly, and one of the reasons we want to do this is we are starting some work looking at structured surfaces where a texture has been imposed onto the disc, and we want to see if we can video that under lubricated conditions. As I say, we haven't tried that yet. I don't see any reason why it shouldn't be successful, but we will find out if it works. So if you want to be updated on that, then get in touch and we can make sure you're informed at the due time. And finally, yeah, it's the same question actually, from Peter Lau. Forgive me if I've mispronounced that. And did we do the test lubricated? No, we didn't. That was dry. And will a lubricant affect the image quality? We don't know, is the straight answer. It maybe will do. So we'll see how we get on with that. And there's another question that's just come in, and I really will make this a final one, from Jacob Suku Morum, and it's about the online measurement. The resolution of the camera, we've got 1,000 pixels, and it's 2 micron resolution per pixel, so that's about 2,000 microns. So it's a couple of millimeters across, in fact. And you are right that you do have to think about the relationship between the area you're viewing and the overall area. We can change that, of course. We can reduce the magnification and look at the entire wear scar, but you can't do everything in one go. So we do need to think very sensibly about what you're doing.
Carlos here again. Thank you very much indeed to Mark, and thank you especially to those people who asked questions. Again, If you have a question that you haven't asked, please send it in, and Mark will attempt to answer it, if not at the end of the next part of his talk, then through broadcast via some email, text later on. We'll talk about that in a bit. So I'm looking at the clock at the moment. It's 12:56 in the UK, and I'd just like to highlight that we will carry on irrespective of the fact that this was supposed to end at 1 o'clock our time in 4 minutes. I think Mark hasn't got much more to say, and this would not be the right moment to let the machine pull the plug on us. So back to Mark to carry on with the third part of his talk.
I wanted to introduce a project called MAIDS to you, and MAIDS stands for it's so important to make up acronyms nowadays. Measurement and Assessment of Durability of Engineered Surfaces. It's funded from something called European Metrology Research Programme, EMRP. It's funding mainly for national measurement institutes in Europe, I should have said there, with some funding through Research Excellence grants, regs for academia and institutes. This project started almost 2 years ago now. It has partners throughout Europe that are listed there. It has unfunded partners as well as funded partners. We have 2 reg grants with Southampton University and Imperial College. The work plan is, the main purpose of this project is to improve metrology for tribological testing, is to develop techniques for small wear volumes, measuring small wear volumes, and this is related to acceleration of testing. If you can't accelerate, then you have to measure small wear volumes, and the main technique we're using is relocation profilometry, AFM and SEM, improved friction measurement, improved interface temperature measurement, feasibility of using Raman to assess chemical changes at the wear interface, and work on monitoring degradation of wear surfaces. So examples of what we've done here are we now developed a self-zeroing friction measurement system for low friction materials. Drift of friction measurement is an issue that we're hopefully getting over. Measurement of temperatures at wear surfaces, and we are doing that at the wear surface itself using sapphire probes. And as I said, relocation profilometry for the measurement of small wear volumes. 2 examples of work: relocation profilometry. Here we put an indent into a surface, and you can see here the indent, Vickers indentation, and the uplift around that, and that's before a tribological test. Here we put a scratch through that, and we actually subtract, this is height information, we actually subtract the initial before image height information from the after height information, and the profiles taken actually vertically across this end of the wear scar, so as a substantial improvement in the quality of the data for the subtracted information compared to the raw information. So that makes this measurement, in theory at any rate, much more accurate than the red one here. We've yet to quantify the uncertainty in that, but it's looking quite promising. And secondly, this is actual temperature measurement of the wear interface as a test is carried out. So the spot there is actually the contact zone, looking through a sapphire window at the contact interface, and here you can see the temperature profile as we step the load up by 10 Newton steps up to a maximum of I think that's about 50 newtons at the top here. So we're now generating an average temperature in about a millimeter spot in this experiment of 66 degrees. The next step here is to enable us to focus on the actual spot there, so that we can get we can have a look at the actual asperity level interaction between the 2 surfaces. So this is still work in progress, but it is already yielding some significant information, because estimating the flash temperature or the contact temperature is very difficult in this sort of condition. So that's it. Just to summarize the whole presentation, not just that element, friction and wear are very complex. You have to keep testing relevant to the application. It's very important, in my view, to match the mechanisms and applications in the application and your testing, and to develop understanding of the mechanisms of wear, which helps to feed back into development of better materials and better design of your components. I'll just put a few links to organisations in the UK that have significant expertise in tribology as a way of linking you up to expertise that is around. So the IIT, for instance, IOP, IMECI, IOM3, professional societies, they all have information on tribology that is very useful, and they all are sources of expertise that, if you need it, people are very willing to talk to you about those, and you will get those links when the slides are sent through to you. So that's it. Thank you very much for attending.
Okay, thank you very much, Mark. And what I'd like to do now is just do the wrap-up phase. And so hopefully everyone can hang on for just a moment so you can see where we go from here. Now, let me show this slide. There we go. So hopefully everyone can see my screen now. So next steps, other than what Mark just told you. Firstly, if you want to access a set of Mark slides, please contact Shelley Sharma at the address you can see there. In addition, if you'd like to be on an email list that will be intermittently updated with things that might be useful for you to know about the progress of the activities Mark has been described, then likewise send a request in to Shelley. Otherwise, of course, you can always try and contact Mark at the address given, or myself, and we'll try and keep you up to date. Shelley is always going to be more expensive than Mark and myself in the first instance. Secondly, the questions that have been posed and some formal written answers to them, we will try and pull that together and make that available either by email or by some download means over the next few days. Third thing, of course, NPL does a lot of events. One of the major activities here is to try and make sure that the experience and the capabilities of the research groups here is available to the UK and, of course, to the world. So a large number of face-to-face events, lots of publications, lots of web resources, and, of course, quite a large number of webinars that go on. So what I'd invite you to do is to keep in mind that we have other webinars coming up. One of them, and the two of them are fairly soon, both to do with piezoelectric materials, so not necessarily relevant to this audience, but if you have colleagues who are working in actuators, oscillators, energy harvesting, then you might want to flag up that we have a couple of our researchers talking about these topics, one about MEMS-scale piezoelectric materials and one about metrology for very high temperature piezoelectrics. So the last thing then is I'd like to invite everyone who's still on the line to send in any questions, any comments, any suggestions regarding this webinar. What was good for you, what was bad for you, what was useful to you, what would you like to see in a follow-up webinar, and we'll capture those and use that to plan what we do next. Now, I don't believe that we have any immediate questions that are coming in that would be very important for Mark to try and deal with now. Maybe everyone's a bit tired and thinking about lunch. So what I'd like to do then is to say thank you to everyone who's taken part. It's been a good experience, I think, for us, and we've had some good questions. We hope that this is the beginning of a long-term relationship. I'll leave the webinar running so that we can capture any more comments and suggestions, but as far as microphones are concerned, this is where Mark and I sign off. So thank you and goodbye from Teddington.